When we talk about artificial intelligence, we picture code, neural networks, and digital minds floating in the cloud. We marvel at chatbots and software but forget the physical world beneath the digital surface. Behind every AI breakthrough is a foundation of real tangible materials, elements mined from the Earth. The AI revolution isn't just about clever programming, it's about geology. The entire edifice of AI rests on rare, specific, and often overlooked elements. Without them, the digital dream collapses. We celebrate the software, but rarely mention the geologists, metallurgists, and mining engineers. Yet, their work may shape AI's future more than the next algorithm. The real limits to AI aren't just in our imagination, they're in the finite resources of our planet. So let's pull back the curtain and look past the glowing screens. To understand AI's true backbone, we must journey deep into the Earth. Trace the supply chain of an AI thought and you don't end up at a server farm. You end up in a mine, holding a piece of rock. That rock, humble and unassuming, holds the key to everything. The story of AI is as much about atoms as it is about algorithms. What are these magical materials? They're not rare because they're scarce, but because they're hard to extract and purify. These elements, rare earths and critical minerals, are the secret ingredients of high technology. Each has unique atomic properties that make it irreplaceable for certain jobs. For decades, they've powered our smartphones and green tech. Now, they're the backbone of AI's physical infrastructure. Data centers, the brains of AI, depend on specialized alloys, unique metals, and specific elements for memory chips and cooling. The cloud is built on a very solid ground. The AI boom is also a mining boom, for things like neodymium, gallium, and even helium-3. Their availability and cost will shape AI's future more than 1,000 lines of code. The periodic table is the new map of power and progress. Let's talk robots, the physical form of AI. Their strength and precision come not just from software, but from powerful electric motors built with neodymium magnets. Neodymium is the secret to creating the world's strongest permanent magnets, enabling smaller, lighter, and more efficient motors. This is critical for everything from robotic arms to drones and surgical robots. Neodymium magnets also power the hard drives in data centers, moving read-write heads with microscopic precision. Every AI data request flexes a neodymium muscle. If neodymium becomes scarce, the cost of robots, drones, and AI storage skyrockets. You can't patch a magnet shortage with software. The physical expansion of AI, its ability to move, build, and interact, depends on a steady supply of this shiny, silvery metal. The dream of a robotic future is tethered to the global supply of neodymium. Without it, progress grinds to a halt. The future of robotics is written in the language of geology. AI's reach is only as strong as the metals within our reach. If neodymium gives AI its muscle, gallium gives it its senses, its ability to see and communicate at light speed. Gallium, when combined with arsenic, forms gallium arsenide, a semiconductor that excels at converting electricity into light. This is the foundation of photonics, using light to process and transmit information. As AI grows, it needs to move massive amounts of data, and copper wires can't keep up. Fiber optic cables, powered by gallium-based lasers and sensors, are the backbone of the internet and high-performance computing. Gallium enables the optical interconnects that let AI models shuffle petabytes of data efficiently. The speed and efficiency of advanced AI systems are tied to our ability to manufacture these photonic chips. A shortage or price spike in gallium throttles AI's potential. The most brilliant algorithm is useless if the hardware can't keep up. To let AI think faster, we need the element that lets it speak with light. Gallium is the gatekeeper for AI's superhighways of information. Now, to the frontier of computation, quantum computing. Quantum computers could solve problems beyond today's supercomputers, but they need to be kept near absolute zero. That's only possible with helium-3, a rare isotope. Helium-3 isn't found naturally on Earth in useful amounts. Most comes from dismantled nuclear weapons. Our supply is tiny and shrinking, with dreams of mining it from the moon. The quest for quantum supremacy is chilled by cosmic scarcity. The next generation of AI, quantum AI, depends on a few liters of this rare gas. No matter how brilliant your quantum algorithms, without helium-3, you don't have a quantum computer. The future of this technology is tethered to the radioactive decay of Cold War relics and lunar dust. Sometimes the bottleneck isn't code, it's a vanishing isotope. For decades, Moore's law promised exponential growth in computing power. But Moore's law is a law of factories, not of the Earth. You can't double the world's supply of neodymium or gallium every 2 years. The exponential demands of AI are colliding with the finite realities of mineral extraction. Software can scale infinitely, hardware cannot. If you run out of a critical element, you can't code a new one into existence. New mines take years to develop, and resources are unevenly distributed across the globe. A handful of countries control most of the supply, making geopolitics a key factor. The limiting factor for AI's growth may soon be the price of gallium wafers, or the availability of neodymium magnets. We're moving from intellectual constraints to physical ones. The digital world is discovering its very real, very earthly cage. The next bottleneck isn't in the code, it's in the ground beneath our feet. The future of AI is grounded in geology. So where does this leave us? At a pivotal moment to shift our perspective, the real forces shaping AI's future lie in the physical world of elements and minerals. The next breakthroughs may come from recycling neodymium, discovering new compounds, or extracting rare earths from unexpected sources. The real gold rush might be led by materials scientists and geologists, not just coders. Software is the engine, but materials are the fuel. As investors, engineers, and citizens, we must pay as much attention to the periodic table as to the stock market. Ask not just what AI can do, but what it's made of, and where those materials come from. Every transistor, magnet, and laser is a piece of the cosmos, rearranged by human hands. The AI revolution is a testament to our mastery of both logic and nature. To truly grasp the future, look beyond the code to the atoms that make it possible. The real gold rush isn't just in the cloud, it's rooted in the resources beneath our feet. The next age of AI will be written in the language of the Earth.